Welcome to this explainer on what is absolutely the defining transition of our century. We are moving from a dwindling fossil fuel inheritance to a steady, continuous, renewable income. It is a monumental shift, and today we're going to break the whole thing down.
Here's a quick look at our agenda. We'll be hitting 1. The new energy age. 2. The mechanics of wind. 3. Harvesting solar power. 4. Taming and storing current. And finally 5. Balancing the smart grid. Let's get right to it.
Section 1. The new energy age, shifting from scarcity to abundance.
Okay, let's dive into this. For the last 2 centuries or so, humanity has essentially been living off an inheritance. Think of fossil fuels like this hidden chest of gold we just happened to stumble upon. We spent it lavishly, right? We built incredible industries and cities. But, that chest is finite, and the hidden environmental costs are really starting to catch up with us. Renewable energy, on the other hand, is completely different. It's more like a steady, continuous income. The sun and the wind, they don't deliver all their wealth at once, but they do provide it constantly, day after day. It's a true partnership with nature, rather than just violently extracting resources.
And look, you might think this is a sudden, out-of-nowhere idea, but just look at this timeline. Our relationship with these natural forces is built on literally centuries of curiosity. I mean, as early as the 7th century, Persian vertical axis windmills were already grinding grain. Fast forward to the 19th century, right in the thick of the industrial age's coal boom, and you have pioneers like James Blythe building the very first wind turbines for electricity, and Augustin Mouchot experimenting with solar-powered steam engines. Then, the 1970s oil shocks hit, and suddenly these fringe ideas became a matter of absolute national security. And today, here in the 21st century, we've seen these unprecedented drops in technology costs that make renewables not just environmentally ideal, but financially inevitable.
Section 2. The mechanics of wind, capturing the invisible current. So let's look at the literal gears of this transition. How do we do it? First, you have these massive aerodynamic blades, which are actually shaped a lot like airplane wings, and they capture lift from a gust of air. They aren't just getting pushed around, the pressure difference literally pulls them into motion. Now, this turns the central shaft, but it turns it very, very slowly. We're talking maybe 10 to 20 revolutions per minute. Obviously, that's way too slow to make electricity. And that is exactly where the gearbox comes in. It acts as this crucial translator of speed, taking that slow, heavy rotation and accelerating it up to thousands of revolutions per minute. Finally, that rapid, high-speed motion feeds directly into the generator. And what actually happens inside that generator is based on a core scientific principle called electromagnetic induction. Basically, that fast-spinning shaft from the gearbox drives magnets past coils of copper wire. This changing magnetic field physically forces electrons in the wire to move, creating a flow. So this is the exact moment, the exact spot where the kinetic movement of the invisible air is transformed into the electrical current that powers your house. And this brilliantly illustrates the whole point. The wind speaks in this wild, unpredictable language of motion, right? While our modern world speaks in the very structured language of electricity. Well, the turbine stands right in the middle between them, seamlessly interpreting those gusts and breezes into currents and volts. Moving right along to Section 3, harvesting solar power, turning sunlight into electricity. To really grasp solar power, you have to understand the photovoltaic effect. This was actually discovered way back in 1839 by Edmund Becquerel. Basically, it's a process where sunlight strikes certain materials, mostly silicon, and literally knocks tiny electrons loose. Imagine this microscopic stage where incoming photons are just setting electrons dancing. And because of how these silicon layers are engineered, those freed electrons get guided along a specific path, creating a steady electrical current. The crazy part? It completely bypasses the need for any moving mechanical parts whatsoever. Let's move to and see how this builds. A single solar cell on its own only produces a tiny trickle of power. But when you wire a whole bunch of them together behind protective glass, you get a module, which is what we usually call a solar panel. Then you link those modules together to form an array. This is exactly how you scale up from a single panel powering a small remote cabin to vast communities of modules generating power at a massive scale. It's how we build those giant shimmering solar farms you see out in California's Central Valley that can power tens of thousands of homes. But hey, photovoltaics aren't the only way to harvest the sun. There's also solar thermal. So while photovoltaics convert light directly into electricity,
Solar thermal captures the sun's raw heat. They use these vast fields of mirrors at facilities like the Ivanpah plant to concentrate sunlight onto a central tower, creating extreme heat. This heat boils water to make steam, and that steam drives traditional turbines. It's amazing because it proves that the sun's heat alone is intense enough to run entire power stations. But all of this brings up a really critical question. The sun goes down, and the wind eventually stops blowing. So how do we translate nature's wild, variable languages into the steady rhythm that our homes and hospitals actually understand? If you're enjoying this deep dive, please like and subscribe to Knowledge Lighthouse to help us bring more truths to light.
Section 4. Taming and storing current, the quiet enablers of the grid. First up is the inverter. Solar panels produce direct current, or DC, but your toaster, your washing machine, the entire national grid, they all run on alternating current, or AC. So the inverter is this crucial device that translates and reshapes that steady stream of DC into the oscillating wave of AC. Without this translator, the power we harvest from nature would remain totally isolated and completely incompatible with the modern world.
Next, we have to actually bottle that energy. We all know about lithium-ion batteries, which are absolutely fantastic for short-term, instant balancing on the grid. But energy storage goes way beyond just batteries. We use pumped hydro, where excess daytime power pumps water uphill, relying on gravity to generate power later when that water is released. There's compressed air stored in massive underground caverns. There are flywheels that store energy as intense kinetic spinning motion. There are even experimental systems out there using cranes to stack heavy concrete block towers, storing energy as potential height.
So the crucial point is that storage is the exhale to renewables' inhale, the release that balances the capture. It completely changes the narrative by bridging the gap between nature's unpredictability and our human expectations. It provides this profound resilience so that a bright, sunny afternoon can literally keep a hospital humming right through midnight.
Section 5. Balancing the smart grid, turning unpredictability into harmony.
Managing the modern smart grid means evolving rapidly. It uses real-time sensors to track shifting wind and solar outputs instantly. It uses something called demand response, where flexible smart appliances, like freezers or car chargers, subtly adjust when they pull power based on what's available on the grid. It handles two-way power flow, allowing a typical home to actually act as a producer and export energy. And it relies heavily on long-distance transmission, like the CREZ corridors in Texas, to instantly shift power from rural areas where wind is abundant straight into demanding urban centers.
Now, what's really interesting about this slide is the massive shift in philosophy. For a century, the grid was just this rigid one-way highway. Power plants pushed energy out, and consumers blindly took it. But today, it is evolving into a dynamic, improvisational network. It acts more like an orchestra conductor, balancing diverse instruments into a single symphony by actively integrating millions of tiny inputs and outputs. This turns households from passive consumers into active, vital participants.
Which leaves us with one final, truly profound question. Decades from now, will we be remembered as the generation that clung desperately to the extraction and fire of the past? Or will we be the one that finally learned to capture the sky and live in harmony with the elements? For the full analysis, grab your copy via the link in the description. Please share this video and check the description for more details.